So let me calculate the moment of inertia for a hoop around its center of mass, and then the moment of inertia for a solid disk about its center of mass, and then the rest of them, you can look them up there in various tables in different books, and our book has enough of them. So there is a table that includes a few of them, like probably 8 or so. So let me erase here, and then get to that. So for the moment of inertia of a hoop, about its center of mass. About its center of mass. Cm is center of mass. So here's a hoop. Looks like this. And imagine it's spinning about this axis. The hoop just rotates about this axis. So all the mass of the hoop, all the material is here, right? It's on the end. The material is here. And all of it is located at a distance r. So here is approximately a hoop, this wheel. Because most of the mass is on the rim. The spokes here are kind of negligible mass. So approximately it is a hoop. And it rotates about its center. So I want to know what the moment of inertia is. Well, let's say the hoop has a radius r. All the mass is located at the radius r from the circle. So let's see. So here is a mass dm. Here is a mass dm here. How much mass is contained there? Well, first of all, the hoop has 2 pi r. The length is 2 pi r. So lambda, the moment of inertia per unit of length, lambda will be the total mass divided by 2 pi by 2 pi r, right? Because if you cut this and open the hoop will look like this. It will be a length L, and that length L is 2 pi r. That's how long. Just imagine you open it. Okay? And now close it back. Okay. So how much mass is contained here into a dm? Well, if this is, the angle here is d theta, then the mass here, then the length, this length here, this length, dl, or ds, I think we usually call it ds. This is r. It's equal to r times d theta. It's r d theta. So the dm will be the lambda times the length of this arc. Will be the length, lambda times the length of this arc. Lambda is m over 2 pi r, right? That's the mass per unit of length, per centimeter or per inch or whatever, times the length itself, how many inches you have or how many centimeters. The length itself is ds, which is r times d theta. Is r times d theta. So you can see here, dr cancels. So dm will be m over 2 pi d theta. So let's calculate the moment of inertia. So the moment of inertia would be the integral of r squared times dm, and then integral. I will write the limits in a moment. R squared times, what's dm? It's m over 2 pi d theta. It's m over 2 pi times d theta. Now, where does theta run? How does theta run? It runs from where to where? Well, if you start here, to account for all the mass, you have to go around the circle once. So that's from 0 to 2 pi. So you have to go from 0 to 2 pi. So let's see. So you get the moment of inertia for a hoop about its center of mass. You have to specify always. R is constant. The distance from here to here, it's always constant. It's the same. So it will be r squared m over 2 pi. This whole thing is a constant. And then you integrate from 0 to 2 pi of d theta. And the integral from 0 of d theta is theta. Evaluated at 2 pi is 2 pi. Evaluated at 0, you get 0. So So it's just this thing times 2 pi. So it'll be r squared, let me write the m first, r squared over 2 pi times this integral, which gives you 2 pi, and that gives you just mr squared. So for a hoop, the moment of inertia for a hoop, about its center of mass is just mr squared, which makes sense, because by definition, the moment of inertia, remember, let me put it in the summation form, it's mi ri squared, and you sum it. But each mass, each mi, this is mi, is located at exactly, r doesn't change, it's located at exactly r. So when I say ri here, for this case, ri is a constant, it's just r, so it would just be r squared, and then you sum over all the masses. So if you add all the mass elements, you just get the total mass, and this becomes the total mass, so you get r squared times the total mass, and that's that. And that makes sense, because every little bit of mass is located at exactly r away from the center of rotation, so that's okay. All right, that's good. Now, how about for a disk? For a disk. So this is for a hoop, and again, these would be provided for you in a test or something, or a homework. You can look it up in the table, but it's not something that you would memorize. Although by using them enough times, you will end up memorizing it. I do have a few of them memorized. So now let us look for a disk. Here is a disk. So now the mass of the disk is rotating about this axis, right? And so it spins about the center of mass. And let's say the disk has a mass m. Disk of mass m, and it's uniform disk, and radius capital R. Capital R. All right? So the way we're going to do this, we will use the moment of inertia. I will be the integral of r squared times dm. The way we're going to do it is, let's go a distance r here. This is r. And I'm going to find a ring here. I'm going to take a ring of thickness dr. The ring will have a thickness dr. So this whole ring is like our hoop, and it has a thickness dr, and the question is, how much mass is located within this ring? How much mass is located here? What's the area of this ring? Right? How much mass is located there? Well, first, when we dealt with a line, we defined linear density. If you deal with the volume, you have the volume density, mass per unit of volume. If you deal with an area like a disk, it will be the mass per unit of area. That's called sigma. The sigma, it's the areal density. Sigma is the mass over area, the mass per area. And the total mass here is m, and you spread it over the entire disk. The disk has an area of pi capital R squared, pi capital R squared. So dm, a little bit of mass within an area dA, will be sigma times dA, times the area dA. So the question is, what's the area of this ring of thickness dr? Well, imagine you have a ring like this, cut it and open it. You will have a strip that looks like this. The length of that strip, if this is r, if you open it, it will be 2 pi r. That's the length, 2 pi r. And the thickness is dr. So what's the area? Well, length times width, that's dA. So dA will be 2 pi r dr. And so dm would be sigma, which is capital M over pi r squared times dA. But dA is 2 pi r dr. It's 2 pi r dr. Notice capital R is the radius, is the outer radius of the disk. So that's a constant. But r changes, right? If I'm using this ring or I'm using this ring, I'm going to add all those rings. So pi cancels, and I get 2 capital M over r squared times r dr. That's dm. let's write down now our moment of inertia. The moment of inertia will be the integral of r squared dm, okay? And I will write the limits in a moment. So I have the integral of r squared times dm. But what's dm? dm is 2 capital M over r squared, 2 capital M over r squared. I write them outside the integral because they're constant. And then the r dr, they will be inside because they are not constant. Now, where is the mass found? Well, the mass is found between 0 and r, from 0 to capital R. Beyond capital R, there is no mass. So we integrate from 0 to capital R, and you get 2 capital M over r squared times r squared times r is r cubed, and the integral of r cubed is r to the 4th over 4, evaluated between 0 and capital R. And well, you get here 2 over 4 becomes a half, and then here I have mr squared times, and then when you plug in r here, you get r to the 4th, and then the lower limit is just 0. And then r to the 4th over r squared is just r squared, and therefore the moment of inertia would just be 1/2 mr squared. This is for about the center of mass for a disk. Remember, for a hoop, about the center of mass for a hoop, if the hoop has a mass m, then the moment of inertia is mr squared. The disk has a factor of 1/2. And the reason for that, for the hoop, all the mass was far away. It was all at a distance r. But for a disk, some masses are at almost 0, and some masses are at r, and everything in between. So it kind of, it averages. You have to do the integral to figure exactly what it is. In this case, it was just half of mr squared. Now, there are other things. If it's a cylinder is like a disk, but you have a stack of disks, but all of them are at distance r. So for a cylinder, it would be exactly like a disk. It would be the moment of inertia for a cylinder about its own center of mass. You can have a solid sphere, I for a solid sphere. Solid sphere is like a bead, or a ball, and it's say you take a metal ball and it's full of mass throughout, and it's spinning about its own center of mass, right? Right here is a ball, and it has radius r and mass m. The moment of inertia turns out to be 2/5 mr squared. And so all of them have this factor of mr squared. What's different is a 1/2 or a 1 or a 2/5 or a 3/5 and so on. It depends on the object itself. Okay. And earlier we did for a rod, for a long rod, about the center of mass, it was 1/12 mr squared, or ml squared. And when we did it about the one end of the rod, it was, I think, 1/3 ml squared. So it will depend on what axis you're rotating about. Okay, I want to show you another example here. Let me erase the board first, and then write the example, and then start recording again. So here is an example. They say you have a 1 meter long 200-gram rod is hinged at one end and connected to a wall. It is held horizontally and then released. And then they say, what is the speed of the tip of the rod as it hits the wall? So let me just show you. So here is the rod. It's 1 meter long, so it's like a 1 meter stick. It's hinged here on one end. It's held. Initially, the speed is 0. So, and then it falls. Boom. When it's at the end, so I think I was blocking your vision. So let me just come here. As it falls, what is the speed of the rod when it is in the vertical direction like this? So it starts here, boom, and then it hits. What's the speed of the tip of the rod, the bottom? We talked about the concept of the center of mass. When the rod is here at the top, the center of mass is here. So what kind of energy does it have? It has potential energy. When it drops, the center of mass will be here, right? The center of mass will be there. So let's say at the beginning, the height, y initial, is 1 meter. But then at the end, y final is equal to 0.5 meters, right? The center of mass will be here. So it lost potential energy, but it gained kinetic energy. And it gained kinetic energy in terms of, here you have rotational kinetic energy. I mean, you could go back and divide it into many, many masses, but let's deal with rotational energy. And here we have the rod here is hinged about its left end, and therefore the moment of inertia will be the moment of inertia for the rod about its end. So remember, for a rod, the moment of inertia about the center of mass for a rod, it was 1/12 ml squared. But the moment of inertia about the end of the rod, which we have here, the rotation is about an axis at the end of a rod, it was 1/3 ml squared. And that's what we're going to use in this problem, because the rotation is about an axis through the end here. You're pinning it here and letting it spin. So we will say, as it rotates, so we have the total energy at the beginning, total mechanical energy at the beginning should equal to the total mechanical energy at the end. The mechanical energy at the beginning could consist of kinetic energy at the beginning plus the potential energy at the beginning. And then at the end you get the kinetic energy at the end plus the potential energy at the end. At the beginning there was no kinetic energy, there was no motion. So that's 0. At the beginning, there was potential energy, so that's mgh, or mgy, y initial. At the end, the kinetic energy is 1/2 I omega squared. It's all rotational, 1/2 I omega squared. And at the end, the potential energy was mg, y final. So let's move the y final here. So you get mg, y initial minus y final will equal to 1/2. The moment of inertia for a rod about its end is 1/3 ml squared, and then times omega squared. So the mass here will simply cancel, and I have y minus y initial, that's 1 minus 0.5, is equal to 1/2 times 1/3 is 1/6. The length of the rod is 1 meter, so 1 squared. The length of the rod is 1 meter, and then the omega is omega. I'm looking for it, omega squared, and therefore I get omega equal to. Let me get my calculator here, and I get what? 0.5 times 6 square root. So that's the square root of 3, basically. Yeah, square root of 3. I did the cube of 3. 3 to the 1/2. I get 1.732. About 1.732. 32 radians per second, not seconds. Let me just make sure I have it correct. I didn't make any mistake. And well, they left it in. All right, that's fine. They didn't plug in the numbers until the very end. And I actually, of course, I made a mistake because I forget the g here, which is 9.8. 9.8, I forget that. So let me redo it. So 9.8 times 0.5 times 6, and then you take the square root. Let's do that. 9.8 times 0.5 times 6, and then take the square root of that. That gives me 5.422. 5.422. That's omega. And then, so what's the speed? Well, the speed depends on what point you're talking about. If you're talking about this point, it has a speed of 0. It hasn't moved. The point that's farthest will be moving fastest. And the speed, as usual, is omega times r, how far you are from the point of rotation. Omega is 5.422. And then the end of the rod is, well, the rod is 1 meter, so it's 1 meter away from here, so times 1. that's 5.422 meters per second. Meters per second. And so I'm going to, now in the next video, I'm going to, let me see how much time is left, but I have to show you why I will prove to you the parallel axis theorem to show you how the moment, once you know the moment of inertia about the center of mass, you're done. You don't have to work, well, you have to do a little bit of work, very simple, but you don't have to calculate it from scratch. Once you know it from the center of mass, you're done. So let's see. So let me show you the parallel axis theorem. I think I have enough time to show it. Yeah, so that should be enough. Let's get to it. Where is my... here. Let me call it the parallel axis theorem. I'll show you why it works. So the parallel axis theorem says the following. So suppose you have a mass here, an extended body. And here is the center of mass. Let's say that's the center of mass, right? Or let me just come here. Yeah, let's say here is the center of mass. And let's say I know the moment of inertia about the center of mass. We know it to be I center of mass. Okay. For example, the rod, we knew it at the middle. We knew it from the center of mass. So now if I come along and I say, you know what, I'm going to fix it here. I'm going to drill a hole here and make it spin. What would the moment of inertia about this axis be? What would it be? So let's say this axis is parallel. You see this axis and this, the axis through the center of mass and through this axis, they're parallel, so it's called the parallel axis theorem. Let's say they're separated by a distance d here, a distance d. Okay? And so to calculate the moment of inertia through this, I have to find the distances here. I'm going to call them RD to here. So which they happen to be from the center of mass through here, our center of mass. So that means D plus RD equals to our center of mass. Let me just, so this is now, we know it. Now, I want to know the moment of inertia about this new axis D, about the new axis D. So first of all, you have this vector plus this vector equals to our center of mass. Parallel. So I have this vector D plus the vector RD. The vector D is the position of this parallel axis with respect to mass, to the center of mass. The center of mass would be my origin. That's the origin, so it's 0. That's my, or going to choose that to be the origin and measure things from there. So D plus RD, RD is the distance of the little masses that I wish to calculate their moment of inertia with respect to this axis. And RD is equal, well, D plus RD is equal to our center of mass, is our center of mass. And therefore RD would be our center of mass minus this D, minus this vector D, minus the vector D. So the moment of inertia with respect to this new D, by definition, it's the sum over mi Ri squared. And the R's are measured from the D. So it would be the sum, of course, from I equal to 1 to n or infinity. So mi Ri is the distance from here to here, and that's the vector RD. And so this becomes the sum over mi, oh, I'm sorry, RD squared, I should say, RD squared. And yeah, let's find out what RD squared is with respect to these. So RD squared. Remember, when you square, the square of a vector is just the magnitude of that vector squared. It's just RD squared, just the magnitude squared. And the way you square two vectors is you take the dot product of that vector with itself. So what's the dot product of RD with itself? That's RD squared. How about here? If I take the dot product of R center of mass minus D and dot it with itself, it would just give me the R center of mass squared plus d squared. It's just the way you square two things, and then minus the dot product of d dotted with r center of mass. That's how it would be. All right, that's how it would be. Just take this. I want you to, if you have time, just do it on your own. R center of mass minus d and dotted with itself. R center of mass minus d. Or actually, let's just quickly do it. So you put R center of mass dotted with itself, that gives you R center of mass squared. And then when you do R center of mass dot d, oh, I'm sorry, yeah, there should be two here. Yeah, it would be two of them. Good thing I did it. You get negative R center of mass dot d, R center of mass dot d, that's for this part. And then d dot center of mass would be, so I have negative d dot with R center of mass, and then negative d dot negative d will be plus d squared, just d squared, because the vector that itself is just the magnitude of that vector. And so I have R center of mass squared plus d squared, and then R dot d or d dot r, they're the same, so you just have minus 2 d dot r or r dot d, doesn't matter. D dot r center of mass. Okay, that's where that came from. So I have mi, and then rd squared, so that gives me r center of mass squared, I'm copying this, plus d squared minus 2 d dot r center of mass, like so. And yeah, so let's expand this. So I get equals I d will be mi times r center of mass squared. So I have mi, the distance to the center of mass squared, plus mi times d squared, mi times d squared, plus, or actually minus, the 2 will come out, and then I have here mi, summation of mi, and then d dot the r center of mass. Center of mass. That's the distance of each mass to the center of mass. Now, this is the moment of inertia about the center of mass by definition. ID will be the moment of inertia about the center of mass. This one will be, the d comes out, so you have a d squared here, and then the summation of mi. So let me put another equal sign, I d. So I center of mass plus, what's the sum of all the masses? The d is constant, so it comes out of the summation. It's just the same number. Because the center of mass and d, and this new axis, they just have a fixed distance d between each other. So the sum of all the mass is just the total mass. So this just becomes the total mass times d squared. That's the part I want. This is the undesired part, and it should be 0. So minus 2, the sum over mi, r center of mass, and the dot product, the d, since it's a constant vector, I'm going to just take the dot product here. Now, the mass times r to the center of mass will give me the location of the center of mass. And then the center of mass is located at 0, so that's the origin. So this whole part will drop, so that's a 0. This part will drop, and I get the desired, the parallel axis theorem. So let me just show you how to use it. Remember, for a meter stick, the moment of inertia about the center of mass, the meter stick is of length L. So the moment of inertia about the center of mass was 1/12 ml squared. How about if I want the moment of inertia about an axis going through the end? So how far is the end from here to here? Well, d is L over 2 in this case. From the center of mass to here, that's L over 2. So the moment of inertia about this end, or d, the end of this rod, will be I center of mass, which is 1/12 ml squared, plus md squared. M times d squared. But d is L over 2. You have to square it. So you get I through the end will be 1/12 ml squared plus, this becomes 1/4 of ml squared. And a fourth plus a 12th, I believe, is a third. Yeah, because a fourth is 3 over 12. 3 over 12. And 1 plus 3 would become a 4 over 12. So that's, yeah, 1/3 ml squared, as claimed, or as we did earlier. So once you know the moment of inertia about the center of mass, you're done. You don't have to make any more calculations. So I'm done with this. The next thing I'm going to do is torque. So that's the next video.